Today we will be learning about the basics of Kubernetes. Kubernetes is a framework that orchestrates and manages containerized applications. This framework is installed across different servers that will make up what we will come to know as a Kubernetes cluster. Now, 3 key benefits of using Kubernetes include the first of high availability. This keeps our software available for customers at all times. In the past, before Kubernetes was mainstream, downtime would be involved for changes such as software or server upgrades. But in today's fast-moving digital world, downtime is no longer viewed as acceptable by customers. A second benefit is scalability. This allows us to handle an increasing number of customers by automatically adding servers to our cluster when we need them, or removing servers from our cluster when we don't, which helps us control our costs on infrastructure. And the third benefit, self-healing. When a piece of software is having issues, Kubernetes takes steps to try and fix it on its own, when in the past, an engineer would have to log into the server to attempt to remediate the issue. Now, for one of the first Kubernetes components, let's talk about nodes. Nodes are machines, either virtual or physical, on which Kubernetes is installed. These nodes are where applications are run. It's common to use AWS EC2 instances for Kubernetes nodes. A Kubernetes cluster is a set of nodes grouped together that run containerized applications. It's important that we have multiple nodes in our cluster, so in case one node fails, the other nodes can still run our applications. As you can see from the picture, there is a node called control plane or master node. This control plane node is the brains behind Kubernetes and makes all the decisions where to schedule pods. You can also see a worker node, so this is where application software will be run. We want to avoid running non-essential software on the control plane and master nodes. Now, the main reason Kubernetes exists today is because the popularity of containers exploded in software engineering, but engineers needed a better way to manage these containers. A container is a unit of software that packages up code and all its dependencies so the application can run in all different kinds of environments. As you can see on the screen, within a container we have code, the runtime, system libraries, and settings. Some of the things that engineers needed to be helped with is not able to dynamically increase or decrease the amount of containers based on customer traffic. And also, if a container fails, the manual effort is needed to start a new container. Now, a pod is a single instance of an application and the smallest deployable unit in Kubernetes. Since we can't directly deploy a container to a cluster, we use a pod as a wrapper around the container with specifications for how to run the container. As you can see on the screen, within the pod we have the container that has the Prometheus image on it, and every time a pod is created, it is assigned an IP address. A deployment allows us to describe the details and desired state of an application. We can define such things as images to use for the pod, the number of pods or replicas that should be created, and it also allows us to upgrade the application without downtime using something called a rolling update strategy. So pods are actually deployed using replica sets, which are managed by deployments. But since replica sets are abstracted by deployments, we don't need to interact with them directly. So some different configurations we could have on a deployment are a name, which is Prometheus, labels, so these are the labels that will be added to a pod, which are important, and we're going to talk about why soon, and the amount of pods that we want created. And we're going to use the Prometheus image on the pod. So we'll see a replica set is created, and then 2 instances of an application, 2 pods are created. Now, earlier we talked about one of the benefits of Kubernetes being self-healing. This is achieved using something called a deployment controller. This controller constantly monitors the current state of the cluster to ensure the desired number of pods are running and available at all times. So while the controller is monitoring the cluster, it notices that a pod becomes unhealthy. So the controller is actually going to create a new pod and terminate the unhealthy pod to ensure that we have 2 replicas running, since that was what we defined in our deployment spec. A service is a way to expose an application running on a set of pods as a network service. The motivation for having a service route traffic to pods comes from the fact that pods are non-permanent resources and are created and destroyed to match the state of your cluster, as we saw in the previous deployment controller example. Every new pod created has a different IP address. This makes it impossible to route traffic to pods based on pod IP, so we need a way to keep track of pods and route traffic to them. This is where a service comes in. A service keeps track of pods based on pod labels and routes traffic to the pods. So regardless of old pods being destroyed or created, a service always knows where to route traffic. As you can see from the image on the screen, we have our Jenkins service. Within this service, we have something called a selector. The selector tells the service what labels to look out for on pods and route traffic to those pods. So we can see we have the label app equals Jenkins. So when the Jenkins service gets a new request, it's going to route the traffic either to Jenkins pod 1 or Jenkins pod 2, since they have the labels that are the same as the selector. Now, when a customer instance is deployed into a Kubernetes cluster, it's a common practice to deploy them into their own namespace. That way we can logically group Kubernetes objects belonging to that either customer or application. So as you can see, we have a Kubernetes cluster, and then if we're going to create a customer, we'll create a new namespace and then have the Kubernetes objects inside of that namespace. It's important to note that namespaces are not tied to specific nodes. Kubernetes objects within a namespace are scheduled onto multiple nodes. It's a good thing that pods are scheduled across multiple nodes, because in case one node goes down, we have another instance of that application running on a different node to ensure that our products and software stay highly available for customers and is a key part of a fault-tolerant architecture. EKS is a managed service by Amazon for Kubernetes. The reason why a lot of people use Amazon's EKS or Google's Google Cloud Engine to run Kubernetes clusters is because they handle a lot of administrative overhead, such as patching, node provisioning, and updates that come with running certain components of Kubernetes. This saves you a lot of time and allows you to focus your engineering efforts elsewhere. Now, to recap, we talked about some of the benefits of using Kubernetes, such as high availability, scalability, and self-healing, the purpose of different Kubernetes objects, such as pods, deployments, and services, and also why using a service such as Amazon's EKS or Google's GKE is beneficial. Have a good day, everyone.